Today's facilities generate vast quantities of sensor and equipment data. By tapping into this data, we can uncover valuable insights, enabling us to operate them more efficiently. But how do we unlock the value buried in all this raw data? SkySpark by SkyFoundry is the answer. SkySpark automatically analyzes data from automation systems, meters, and other devices to identify issues, faults, trends, and opportunities for operational improvements and cost reduction. With SkySpark, analytic rules run against the data produced by your systems. Through a variety of pattern recognition techniques, SkySpark's analytics engine quickly identifies issues worthy of your attention and provides clear, easily understandable visualization showing those issues, their frequency, duration, magnitude, and cost. And because SkySpark is fully programmable, rules can be adapted to the unique needs of individual facilities. As a completely open platform, SkySpark works with data of all types, whether it be live data from automation systems, meters, or web services, or historical data from files and databases. SkySpark can be used in a wide variety of applications, including energy resource management, analysis and reporting, monitoring-based commissioning, equipment fault detection, benchmarking, performance tracking. SkySpark gives you the insight you need to improve efficiency, reduce energy use and cost, increase occupant satisfaction, and improve the performance of your assets. Visit skyfoundry.com and start finding what matters.
Hello, good afternoon, everyone, and thank you for joining us for today's exciting webinar on machine learning and energy data analytics. My name is Sam Schwartz, and I'm Member Engagement and Marketing Manager for EMA. And today's webinar, as you might have already seen, is sponsored by SkyFoundry and Energy Twin. I'm going to cover a few housekeeping notes before we kick off today's session. We encourage you to submit questions at any time using that Q&A button you see at the bottom part of your screen. We will address all questions at the end of the session, but please don't feel like you need to hold off until then. If you happen to be experiencing technical problems during the webinar, please use the chat function to inform the panelists, and our technical experts will do our best to assist you. This presentation is being recorded and will be sent to all registrants for viewing within 1 week, with also an on-demand quiz for credit. Finally, in terms of continuing education credit, everyone in attendance for the full webinar will receive a certificate of attendance sent to their email within 24 hours. However, please keep in mind that in order to receive credit, you must be logged in using the unique link that was sent to you, not one that might have been shared with you from a colleague. So jumping into today's session, today's webinar is Energy Data Analysis and Machine Learning, Real-World Examples with our experts, Jan s.r.o from Energocentrum Plus and John PETZE of SkyFoundry. So a little bit about our presenters today. Jan's doctoral studies were devoted to fault protection and predictive control. His current research focuses on machine learning for energy and HVAC data analysis. He's the head of the R&D team that develops the Energy Twin tool and Energy Data Analysis tool. He's involved in a number of practical applications of machine learning in the energy sector. And returning for another webinar with us is John PETZE, the co-founder and CEO of SkyFoundry, the developers of SkySpark, an analytics platform for smart device and equipment data. He spent over 30 years of experience in automation, energy management, and M2M2 IoT, having served in senior level positions for manufacturers of hardware and software products. He is also the executive director of Project Haystack.org. So without stealing any more time, I'm going to hand it off to John, who's going to kick off the presentation today. John?
All right. Thanks so much. Appreciate the opportunity to be here to talk about this important subject. Machine learning is a topic that is receiving a lot of attention, a lot of press, a lot of hype, and a lot of buzz. But they're really effective tools that can be used. And what we wanted to do today is to demonstrate the type of real-world results that can be achieved by applying machine learning techniques to energy data analysis. And so I want to start our discussion today with a little bit of background that hopefully will provide a good introduction to the topic. And then we'll be turning it over to Jan. I'd like to start with this comment. I think it's a appropriate comment to say that data is now fundamental to everything that we collectively need to do to address our critical sustainability goals. Data is the foundation for identifying how systems are working, converting that information to greenhouse gas equivalents, to other KPIs. So data is really the foundation that we're working with to address our sustainability needs. And when we talk about data, there are challenges. And let's talk about a few of those. We can easily prove that hidden in the operational data from our systems are the keys to better building and equipment system performance. But the challenge is human beings are not good at analyzing large volumes of raw data. And so in most endeavors, we need tools to help us do that. And analytics software, which has dramatically increased in availability and sophistication in the last decade, is really the tool we're talking about and we're going to present today. Now, analytic tools employ a wide variety of techniques, pattern recognition, advanced math, et cetera. But today we're going to focus on machine learning, which is a very valuable technique that's directly applicable to certain applications in energy efficiency and building system analytics. There's other examples out there, but today let's focus on that because it is of great interest to, I think, the industry. So we'll start with energy data, right? That's critical if we're going to assess and improve our building performance. And what we find now is today, state-of-the-art software applications can utilize advanced algorithms that will streamline the process that was historically done manually. There have been energy analysts working for decades, but there'd historically been a lot of manual effort to accomplish those analyses and uncover relationships and insights. So machine learning, again, while it's not a silver bullet for everything we want to do in building systems, it is much more than a buzzword. And there are numerous scenarios where you can start using machine learning right now to gain the benefits of deeper, more efficient energy analysis. But let's start. If we're going to apply machine learning, step one, we're going to need to acquire data, and that are some of the initial challenges that we face. There are diverse sources of data. There's diverse formats data comes in. There's diverse protocols. It comes in at different frequencies. It comes in real-time data. It comes in as file-based data. It comes from web services, APIs. Many utility companies offer a web service feed where customers can get their energy data. And then, of course, we know there are communication protocols like BACnet and OPC and Modbus and others that are used by the control, automation, and sensor systems that are found in buildings. So step one does start with access. And I guess I would add one other topic to this. Increasingly, cybersecurity is one of the challenges that has to be addressed in connecting to and getting data. So first step, we have to get our data. Second step, let's think about the different types of data formats, right? What we find in the industry is there's different formats that the source comes in. Sometimes it's a very simple format, like the example here, which is called CSV, comma separated variables, right? That can be read quite easily by software applications. But in other cases, there are many other formats that might not be so human-friendly, and things like XML, JSON, Zinc, Turtle, et cetera. So connecting to get the data is step one. Being able to interpret the formats is step two. And one of the key elements involved in doing that is the work that the Project Haystack organization is doing to define standard metadata models for different types of data. But now, let's say we have our data, we understand our data. I want to take us through what I would consider the kind of the journey of working with data. Because in many cases, it starts with manual analysis, and this is not bad. This is where many people start. Manual analysis, where we use charting, graphing, a whole variety of visualization techniques, and we apply our expert knowledge to it. So I'm the expert, I can look at these charts and graphs, and I can determine what these patterns mean, what they lead to, and potentially what types of actions I want to take to improve the performance of my facility. In addition to graphical charting, we would normalize the data perhaps for building size, weather, or other factors. Another common thing we might do with manual analysis is benchmark or baseline, comparing current actual data against historical data for specific periods of time that we want to make comparisons for. So we'll start there, but the next step would be, let's calculate our KPIs, our key performance indicators. And here we start using software techniques to automatically do this for us, to calculate key performance indicators, and then to present them in ways that make it easy for the operator to understand their KPIs and the patterns of operation. KPIs help us highlight energy use peaks, anomalies. They can be used to calculate our actual energy costs based on complex tariff rates. That's an important part of analyzing energy, is to turn it into real money. And oftentimes we might think of an average cost for a kilowatt hour of energy, but typically if you're in a commercial market, you're paying for your energy with fairly sophisticated tariff rates that have numerous charges, and that might be generation, distribution, consumption, demand, time of day, time of year, etc. We need software to do all of the calculations to turn our meter data into real cost based on those tariffs. Increasingly, we want to address the need for carbon reduction, carbon tracking, and convert our energy use into greenhouse gas equivalents. The software can do that for us, right? It can take our meter data and apply the appropriate conversion factors to turn that into greenhouse gas equivalents, which are increasingly required for reporting to regulatory organizations and to be reported in annual reports from corporations. The way we as humans consume this is, of course, with different visualization techniques, charts, graphs, dials, etc., like we see here. But one more point is we need to be able to export both our visualizations and the raw data and the raw KPIs, the calculations. We want to be able to export that for use in other applications, because today in the world we may have many different types of applications that we want to be able to consume the data from different systems, automation systems, analytic systems, etc. But the next step after these manual steps, of course, is to now take advantage of automated techniques, automated analytics, employing advanced AI techniques like machine learning, which is the focus of our conversation today. So we're really fortunate today to have Jan ŠIROKý of the Energy Twin team. Jan and his team are recognized leaders in applying machine learning and other advanced analytic techniques into the built environment, and specifically around energy and performance data. And we're excited to have him join us today to give us real-world examples of how they're applying machine learning. Especially we're excited they're using our technology, among others that you'll see here today, to provide value to building operators so that they better understand their performance and where they can improve the operation of their facilities. So with that, I am going to turn the presentation over to Jan, who will take us through some real-world examples, and he'll start with some really important definitions and explanations of key AI and machine learning techniques. Jan, thanks.
Thank you, John, for a kind introduction. And hello, everyone. Good evening from the Central Europe. And let me start with a quick review of AI and machine learning concepts. So in order to avoid any confusion, let's start with these two terms, these buzzwords. Artificial intelligence is in general capability of machine to imitate intelligent human behavior. This could be done by a simple script or deep neural network. It's a quite general term, this artificial intelligence. A subfield of artificial intelligence is machine learning, and this will be topic of today's presentation. Specifically, machine learning extends the ability of artificial intelligence by learning these things from data rather than being explicitly programmed. And there is also this deep learning and neural networks. This is more advanced topic. We will not be talking about this. We will be talking about this, let's say, basic machine learning. What are the basic approaches in machine learning? First of all, there is reinforcement learning. It works on interacting with the environment. So you can imagine a robot that's navigating through unknown environment, and when he hits the wall, he tries to learn something from that and avoid hitting that wall next time or hitting any wall next time. However, this has minimal practical use in the energy sector. You can find some academical papers. They are mainly focused on simulations, but in the real building, you do not want your heating system or HVAC system in general to make some try and error algorithm in your building. The next big group is called unsupervised learning. In this case, training is using unlabeled data without any guidance. This has some applications. This approach has some applications in energy sector. For example, you can search for similar patterns or some anomaly patterns and so on. But the most useful approach is supervised learning. It means that the model is trained based on the given inputs and its expected output. You can imagine easily this by taking into account temperature as an input and the energy consumed as an output. And the goal is to learn what is the relation between these two quantities or these two data sets that you have. And there are plenty of applications in the energy sectors, and in the following part of the presentation, we will talk just about the supervised learning. And there are two problems that are solved in supervised learning. First is classification. In classification, the goal is to predict a discrete class label. It could be, for example, decision if some machine is in faulty state or if it's normal. And the second class of problems are regression problems, where you are predicting a continuous quantity. So, for example, KW or KWH, temperature, but major difference is that they are predicting quantity, not the discrete label. There are plenty of methods that can be used. Many of them do have some variants for classification as well as for regression. For example, subprovector machine and subprovector regression. In this presentation, we will be using just the linear regression. But the goal of this introduction is to provide this background that even this very simple regression like degree-based model could be seen as a part of machine learning. But actually there are more complex models, as will be presented in the next slides. To provide you some real-world examples of the energy regression models, we can talk about degrees-days models. and also about ŠIROKY change point models. Here is a chart that shows the 5 change point model. On the x-axis is temperature, and on the y-axis slope. And yeah, what we do have here is some slope from the heating in the negative or low temperatures, you get higher load due to heating. Then you hit the bottom. It's called base load. And then if the building is also has cooling, then you have again increase in the energy use due to use of cooling. And there are some parameters that could describe such a piecewise linear function. And the goal of machine learning or regression in this case is to use the measure data in order to identify these parameters that describe the data that you provided. And this is what we are doing here. But I will show you examples that are using much more complex model than this one, but the idea behind it is always the same. You just use your data in order to tune some parameters, and the advantage of regression models is that these parameters are physically interpretable. Before we jump into these real-world examples, I would like to talk about 2 challenges, because some of them could seem as a details or technical details, but they are of great importance. First challenge is data granularity or model timestamp. Usually, you can see degrees days models using monthly data. This is very simple model. You can design this in Excel and solve it very easily. So there's no high computational demands, and you can use different tools for that. However, you will get just a limited insight. It's mainly due to the fact that there's a lot of things going on within the month, and if you sum it on the monthly basis, you will lose a lot of valuable information. You can improve it using weekly data or daily data, but anyway, still a lot of information remains hidden, and therefore it's more you can gain much more insight using hourly data or 15-minute data or even 1-minute sampling. But it has also some drawbacks, and one of the drawbacks is that the model is complex. It can have hundreds or thousands of parameters, so you need more data in order to train your model, and you probably also need some tools that are capable of performing such a calculation. I would like to mention models that are used for hourly data. There is a well-known model that was published by Lawrence Berkeley National Laboratory, time of week and temperature model, TOWT. There's in the square brackets, you can see the name of the paper where it was firstly published. And there are plenty of modifications of this model, and yeah, this model just works. However, it has also some drawbacks. I do not want to go into details, but these drawbacks, for example, are related to handling of discrete variables. And there are alternative approaches, for example, based on decision regression trees. And again, some interesting paper from Lawrence Berkeley Laboratory, when they are using gradient boosting machine for modeling energy data on this high sampling rate. Okay, so the basic message is using hourly or 15-minute data, you can get much more valuable insight here, but you need more advanced tools for that. Here to illustrate this is a comparison of visualization of these 2 models. So on the right side is the 5-point change point model I was describing before. And there are, yeah, as its name implies, 5 parameters. However, on the left side is a slightly modified TOWT model. And this model has approximately 600 parameters that are tuned by this regression modeling algorithm. So you can see the different complexity by yourself. The next challenge I called automation. And as I mentioned in the previous slide, a lot of things can be done in Excel or Google Sheet, but I suggest that many of you have been using Excel, and you have some experience when you get some problems with copy-paste errors and so on, and get some terrible headaches from that. It's time-consuming, and if you use a lot of data, you can also get some problems with update, or you spend a lot of time updating and so on. So there's a lot of obvious disadvantages when talking about this manual approach. We suggest you to focus on dedicated tools that are available. Again, I would refer you to a paper by Lawrence Berkeley National Laboratory. They summarize the tools that are available. They also have some review, a few years old, but still it's a very good guideline for this. And there are also some open source tools available. Some of them do require some coding experience in Python, in R, but there's also Excel sheet you can use. And last but not least is tagging and use of semantic data. This is a major further step in streamlining the process of automation. For example, you can use the semantic description for coupling the data. So if you have a profile with your energy consumption, you do not have to define what is the related weather station, or how is the occupancy defined, because it's probably already defined by some semantic data that do refer to particular points. And you can focus on working with the data results, not configuring all these data together. And you can also use batch processing easily. That also helps if you have dozens of measurements. It's important. And this tagging and semantic data can make use in virtual sensors, in aggregation. I will show you one example in the next slides where we use this, and you can make different sums of sensors or subtract some submeters and so on. And again, this is the field where use of tagging and semantic data can help a lot. John mentioned Project Haystack. There's also brick scheme and so on. So this is something that is helping to streamline the process. Okay, so now I would like to go into the case studies. In all the case studies, we used energy twin model in SkySpark. It's extended time of week and temperature model. It has 2,700 parameters. And I will be focusing on three sets of real-world examples. First one is anomaly detection in an extensive building portfolio. The second is related to COVID-19. And the third one is related to prediction and use of prediction in different scenarios. So let me start with anomaly detection in large building portfolio. We got a customer with more than 150 buildings connected online. These buildings do have different purpose, different size, different regime, different equipment. And the goal of the customer was to have a fast response to anomalies. And frankly, our goal was to deliver this service with minimal effort. So we use historical data for model identification. Each building has individual model, and we continuously compare the online measurement with prediction. And all the anomalies are evaluated by expert in order to avoid any fault, any faulty detection to be sent to the technicians. And if the expert evaluates the anomaly as valid, he starts some communication with technicians that do go to the building and try to fix this. On the right side, you can see the table with some parameters, R² and CD-RMSE. These are two parameters that are required by measurement and verification guidelines, namely IPMVP and ESHRI guideline 14. And this illustrates the importance of batch processing and so on. You can immediately see which models do fit these measurement and verification guidelines. So these are the green ones, while the yellow color indicates that one of the criterions is not met. So you have to be careful when evaluating this model. And now, we are here in the section with charts. So first of all, let me describe what we see here. Blue solid line is prediction, red solid line is measurement, and blue dashed line is threshold. In this particular case, it is defined as a prediction plus 30%. In the first few days, we can see a nice fit. Basically, red line is close to blue line, while in the next days, there is some deviation, and we can see that the threshold was exceeded, and in the bottom, anomaly was detected. It's important to note that this gray area, integral of this gray area could be seen as estimation of available energy. So the amount of energy that we consumed or the building consumed above the threshold. But frankly, you do not want to look at these charts all the time. If you have 150 buildings, you do not have time for that. And you need some overview. And this is it, how it looks. And this is what a colleague of mine every week checks in order to be sure that there is no major problem. And any anomaly is identified by this square, as this arrow shows. And you can sort all these detected anomalies by total duration. But in some cases, duration is not the most important thing. You may be more interested in total kWh. And this is the second column. So you can also sort by kWh and start with the most severe anomalies that you detected. What we have found during this monitoring of a large portfolio. So the basic message is that even such a large portfolio could be checked in a few minutes. So you can do it on the daily or weekly basis. And you can be sure, almost sure, that any major anomaly remains undetected, because it should be detected by these algorithms. And we are not talking about crossing the threshold, like consuming more energy than expected, but also consuming less energy than expected. That could be also indication of some fault in the building. What did we find? You can expect some usual suspects. So manual regime override, local heaters. For us was surprising, for example, this wrong meter current transformers installed. And there are also some funny things. Unfortunately, this is in Czech, but I provided the translation. This is what we received from the technician on site. He sent us this picture or photo of the note saying, turn off the ATM ventilation. And this solution was definitely not working, because we found this as anomaly, because nobody was turning ATM ventilation off. The next section is devoted to evaluation of COVID-19 impact on energy consumption. in this case, year 2019 serve as a baseline. So the last year where things were normal. So model was identified using data from 2019. And there were many questions that we have been trying to answer. So for example, how much energy did we save due to few employees in the building? Or if they start non-stop ventilation, how much energy does it cost? We were facing different comparisons of different sets of branches and so on. I will show you examples in the next slides. Here is a real-world example of one big office building that we have been analyzing. And this is March 2020. And the beginning of this month was the last days, were the last days before the first lockdowns hit the Czech Republic. So you can see the last normal week, the measurement fits the prediction. And now suddenly you can see different profile, namely during the working hours, you can see drop in the measured energy consumption when compared to prediction. And important is this detail where after a few days, they started non-stop ventilation in order to prevent infection. And it has some immediate effect on the energy consumption. So you can see that in the night time, they have some increase in the energy consumption. And this is the next month, April, when you can see this pattern during the working hours, lower energy consumption due to less employees in the building, but in the night time, higher energy consumption due to non-stop ventilation. And there is a summary table on top of this slide, and it provides us the answers to some questions that were raised. So we can easily estimate that during unoccupied periods, we can see absolute difference of 55 megawatt hours of electrical energy. So this is our estimate how much does the non-stop handling unit ventilation cost. And my favorite detail is this one. So if you look at the total difference is just 1%. So if you will use monthly data and using, for example, this degree days method, you will come to conclusion that the total difference in energy consumption is just 1%. So you can say, yeah, there is not a big change when compared to the previous regimes, previous years, but the opposite is true. There are many changes, but by the chance they compensate each other. But when you use this hourly model with hourly sampling, you can have this insight. This is what I had in mind when I was talking about this insight you get when you are using these detailed models. The next example is related to aggregated virtual sensors. Again, we are talking about this big customer with 150 electrical meters connected, and they were asking us different questions about different sets of branches or buildings. And according to applied pandemic restrictions, they were able to define different sets of buildings, and they ask particular questions. So here is an example of one such particular set of, I think, 26 buildings aggregated together. And we were able to provide them quite reasonable answers. In this case, there is a significant drop in the total energy consumption during work hours and almost no change during the setbacks. And this helped them to tune the regimes in the buildings properly and make some strategy optimization during these lockdowns. And the last example from this section is dedicated to shopping malls. These are 3 big shopping malls all from the Czech Republic. So all of them were exposed to the same regimes to the same lockdowns. And first of all, you can see that in the summer, there was, let me start with explanation of these numbers in the cells. So in each column is one particle period. So first wave in the spring, first lockdown, loosening during the summer, second wave in the autumn, and third wave in spring 21. And in each column is the difference from the normal, from the baseline that was 2019. And in the summer, we can see that the things almost returned to normal. So the buildings were consuming almost the same amount of energy as before, as 1 year before. In the case of shopping mall 1, we see that during the first spring, first wave, they consume almost 50%, more than 50% less energy, and they were able to maintain the same level of energy reduction during all the next waves of COVID. But surprisingly, if you look at the shopping mall 3, actually the biggest one from these, they have some exceptional energy savings during the first lockdown, but they were not able to maintain these exceptional savings, and they end up in just 35% energy reduction. And this makes almost 160 megawatt hours per month. So it's even for shopping mall, it's quite significant amount of energy. And they have been asking the questions why there is such a difference. So at one point you can say that 35% energy reduction is quite nice, but the right question is why it was not 60 as a 1 year before. So what is the message from this analysis? First of all, unprecedented setbacks were measured. A lot of buildings were put into setbacks regimes that were not done before. And in many cases, you have this data measured in your building management systems. And it's a very interesting source of data to be learned from. And yeah, you can ask such a questions: what could be switched off when they were able to switch it off during the pandemic lockdown? Why cannot we switch it regularly, and so on? It's important to know that machine learning model here compensates for different weather conditions. So it's different type of comparison than if you are just comparing one month with the other, because you have different weather during these months. But when you are using prediction from this model, the different weather is compensated. So you can evaluate it quite precisely, the differences. And this use of detailed model raises important questions, like I mentioned that 30% energy savings could be nice, but why it was not 50? And the last part of this presentation is dedicated to prediction. Most of the attendees probably from US, and there is this great initiative for energy efficient buildings, and there is a quotation from National Roadmap from Grid Interactive Efficient Buildings that says the prediction of availability of flexible loads over a given time is something that will be required by these grid interactive efficient buildings. So in other words, if the building will be able to predict its own consumption over the horizon of a few hours, it could be used in this concept that make use of flexibility and, as they call it, grid interactive efficient buildings. In short, energy consumption prediction can be used for different purposes, like predicting free power capacity for electric vehicles charging optimization. You can predict energy flows. I will have one example for that. You can optimize battery charging strategy or utilize this prediction within the complex system. I also have one example for that. first of all, this renewables. Here is an example of the building that has some own consumption and PV panels on top, and the blue line is measurement, red line is again prediction, and the positive values are consumption from the grid, while the negative values are the moments where, or indicate the moments where the buildings is sending electrical energy into the grid. It's ongoing project, so the prediction does not fit perfectly the measurement. But what is important is this right side of the slide, where you can see that at some point your blue line ends. So this is now, and you can have a prediction of next few days of energy flow, and you can prepare for that. For example, optimize this battery charging or electrical vehicles charging. And the very last example is quite complicated, and I do not have time to go into the details, but it's related to virtual power plant. This is a project with a utility company where we focus on cogeneration units scheduling tool. So there is, let's say, 15 cogeneration units around the Czech Republic, different cities, and they are usually connected to district heating systems. And the goal is to have maximize the amount of the profit, monetary profit from operating these CHP units according to electrical energy spot prices prediction. And you need to take also into account the heat delivery prediction for each town individually, and also various constraints like technical, legislative, operational. Some CHP units cannot run during the night, and so on. So what were the results? So first of all, there are definitely better results when compared to human scheduling. It's much more profitable. And the reason is quite simple, because human brain simply cannot evaluate all the combinations. Actually, at the very beginning of the project, I was thinking, okay, and if we did not find out anything more convenient, we can calculate all the combinations and find out what is the best. And if you have 24 hours per day and you schedule on off for each hour, in this table, I do summarize the amount of combinations. So if you have one CHP unit, you have 16 million, but if you have 2 units, it's a number I cannot read. And if you have 10, yeah, you cannot even write such a number. So it's quite obvious that a computer or some algorithm can evaluate this more precisely. And one of the side effects or outcomes of this is that it pushes system to its limit within the constraints given to the optimization, but it poses some challenges. So there is, for example, importance of fault detection. And I will illustrate this on contracted maximal daily gas use. So in the Czech Republic, we got a major penalty for exceeding maximal daily contracted gas use. And one of the outcomes was that this virtual power plant was pushing the system into the limits of these maximal contracted daily amounts. And I will show you a screen from the let's say prevention exceeding dashboard, where again we are using prediction. So red line is already consumed amount of gas, and the blue line is the prediction with respect to the typical profile of energy consumption of this city and the weather forecast. We are able to predict that there will be probably some small exceeding at the end of this day. And technicians do have a couple of hours for preventing such a thing to happen. So this help them to be able to be on these limits of these systems. So this brings me to the conclusion. I would like to stress once again the difference between monthly and hourly data. It's a game-changing detail. It's not just a technical detail. Importance of proper software tools, and it's not just about the charts or the different dashboards that you can get and how nicely they look, but it's more about the flexibility of the tool. Because if you start working with these data and some big amount of data, you appreciate more this batch processing and so on, rather than just nice looking charts. Yeah, online connection is of great importance. It's clear, and utilization of semantic data and tagging can help you a lot with streamlining the process. It's important to know that all of these examples I have shown today are from our company. That's mid-sized company, and these are not some visions of multinational corporations or dreams of startup companies. It's a thing that you can start using now. And the last remark is that I'm a fan of these sci-fi, different science fiction movies where machines are taking over, but this is not the case. Machine learning is here not to replace the energy experts. It's here to make them more efficient and be focused on the essential matters instead of doing some dual part of the job. Okay, so thank you very much for your attention.
Okay, thank you so much, Jan and John. Very enlightening presentation, and we certainly have a decent amount of questions lined up. So we have about 9 minutes left, so I'm going to jump into them. The first question we have is, what type of building was being represented in this slide for the energy regression model?
Let me jump back to...
Yeah, it was your first example, Jan, on energy regression. Mm-hmm.
This one or this one. Yeah.
Not sure, but why don't you explain?
Yeah, but I can comment both of these. I think that in this case, this is just an illustrative example, and this is the building that uses energy for heating as well as for cooling. And in this case, this 3D chart, I know this building by heart, is one big building office in Czech Republic. So you can actually, this is the European style of weekday. So we are starting with Monday. So you can see 5 days with higher consumption and lower consumption over the weekend with some small peak on Saturday morning.
Okay.
Okay.
And what's the next one?
All right. I am going to go in order of how they came in, just in case you do need to go back. Next question is, I assume models are not transferable between buildings/sites due to large variability in the variables. Do you train models for a single site using historical data of that specific site?
Yes, this is exactly like that, and this is important to be able to do it like this. It's not the intention to identify a model on one building and try to use it on the other. You should identify a model for each building individually.
Okay, great. What are the best practices regarding handling of time series data for periods of mechanical/controller failure, or when a given HVAC system is not operating according to spec?
John, you can address this.
Well, I won't say the best practices. I'll talk about some tools. data quality tools would be used to detect missing data when it's expected. So you can detect that we've been getting data every 15 minutes and now we didn't. You can overwrite that data with interpolation. You can write in that you have missing data, what's considered NA data. You can also look at magnitude of change and say this is a bad reading and interpolate for that period of time. There are a variety of, I would call, data quality and data markup algorithms that can be used. But again, I think it's similar. There isn't one approach to use for all types of data.
Yeah, maybe I just to remark, and this is very important to remove outliers and invalid numbers from your data set before training the model, because you will get unusable, the model will be not useful, and you will just waste your time. So you cannot skip this part of the process.
Next question we have lined up here. Regarding energy regression models, have you tried clustering the interval data by day type? Once the days are clustered by pattern, each day type is a simple regression according to the time of day. And they put an example of regression for 1 a.m., 2 a.m., 3 a.m., etc.
Yeah, this is one of the possibilities how to construct the model, and it's definitely doable. And for some applications, yes, but we found out that this TOVWT model, is simply just a reasonable combination of parameter setting, and with some enhancements, it serves the best for our purposes.
Okay, thank you, Jan. It's an interesting one. In your experience, do models experience data set shift? As in, do models lose accuracy and need to be maintained often as time goes on?
Yeah, this is crucial question, because you would like to retune your model. So in some cases, we use automated tuning. And again, we are in this flexibility issue. So it's very straightforward thing to do in this tool that we are using. So in some cases, we do weekly or monthly re-identification of the model, but you have to be careful. By doing this, you can learn wrong behavior that you would like to detect. So it's not always the best solution, but in some cases it's definitely useful, especially in some if you have limited amount of data and you need to improve your model as receiving more valuable data by time.
Thank you. And here's a question that's probably been asked many times over the past 2 years. Given our concern for better indoor air quality, how should we trade off energy use for filtration and healthy occupants?
John, can you address this?
Well, I'll comment on it. And David, as we brought this up, I think one of the things we see is, well, if we're going to have better indoor air quality, we're absolutely going to use more energy. That by itself is not true, because you might identify by using analytics that the piece of equipment is not performing adequately to begin with, right? So I think we have to say that, there are multiple factors here. Yes, you can do the calculations that if you bring more air through the system, through the heat exchangers, et cetera, the calculations show more energy. But I think if you take a more holistic look at applying data analytics to that equipment, in many cases, you identify inefficiencies that by correcting them, you'll get to your IAQ goals without increasing your energy.
Okay, good answer. Jan, there was another attendee asking, what model did you use for the energy consumption slide?
Energy consumption slide. To me, I'm not sure which slide you have in mind.
I'm not sure either on which one he was referring to. So maybe if you can throw it in there, we'll move on to the next one and come back. Mahfouz, if you can mention which one. So
but actually in this presentation, all the slides that I have shown were using this energy twin model that we implemented in SkySpark, and this model is based on TOWT model with some extensions.
Okay. Next question. During the energy consumption comparison, how are the prediction values determined? Through energy modeling or normalizing as baseline curve for the same kind of building?
In prediction, you mean? For prediction?
How are the prediction values determined, is asked.
Okay. The most important part is to have some valid weather forecast and also forecast of all independent variables. It means mainly if you have, for example, different model for occupied and unoccupied periods, you need to know occupancy profile in the future. And yeah, if you have this, it's very easy to provide the prediction, and this prediction is the reliability of the prediction is determined by the reliability of your inputs, so by reliability of your weather forecast.
Okay, thank you. And apologies if you did cover this towards the end there, but I'm going to ask anyway. As people continue to come back to more to buildings, is there any significant increase of energy consumption because of extra ventilation during busy hours?
Did you see that, Jan? Did your customers increase ventilation in those buildings after the when they had people come back from the pandemic?
Yeah, actually, we see such a amount of differences in these days or in these months that we cannot evaluate this now because there is mixture of different factors, and it's not so crystal clear as at the beginning. So lockdown is not so strict, at least in the Czech Republic, as was at the beginning. So yeah, we cannot say now.
Okay. Question for John. Are platforms like SkySpark using machine learning to automate the FD&D to help the facilities personnel?
Yeah, absolutely. And as I mentioned, machine learning, as we're seeing, is a very effective tool. It's not the only analytic technique, and you don't always need the most advanced analytic techniques to detect faults for operating staff. Basic pattern recognition of trends, rates of change, correlations and conflicts between items are also used, as is other advanced math techniques, I'd say short of machine learning. But yes, machine learning has a role to play in fault detection for numerous applications. And, it's one of the reasons we include those tools in our software. And, of course, as we've seen, Jan did take advantage of those tools plus others. So.
I'm going to sneak in two last questions. If anyone else has any other questions they're hoping to ask, feel free to submit that to the Q&A. If you did it to the comment section, if you can push that into the Q&A button, that way we can make sure to share it with the presenters afterwards. Are the majority of your charts showed using TOWT type model?
Yes.
Don't know what that acronym stands for. Okay.
Yes.
Great.
Actually, slightly modified, but the basic concept is the same as TOWT model.
Okay. And final question here. Have you used machine learning results to improve controls, such as automating set point changes in real time?
Yeah, this is very, very, very interesting area, and we have been using this, for example, for model predictive control, where we've been using dynamic models for controlling the buildings with slow dynamics, and yeah, for example, thermally activated building systems, and yeah, this is a very interesting thing.
Okay.
One came in on I know we're out of time, but one did come in that I think Jan should speak to. The question was, is SkyFoundry okay to share the programming? SkyFoundry did not do the programming. We're showing how Jan's company Energy Twin used our software with their skill set and programming. And I believe, they offer these types of services on a consulting basis. So I would reach out to Jan at the contact information here shown.
Yeah.
Yes, absolutely. And for any of those questions we didn't get to, I'll make sure to pass those on to the presenters with your contact information so they can follow up. Jan and John, thank you so much for coming on. Do you mind advancing to the next slide? Perfect. Thank you. Okay. To close out, thank you everyone for stopping by for an hour with EMA once again. We are gearing up for CX Energy in April. If you have not registered yet, please be sure to do so. You can save 10% still with CX Energy 10, that promo code right there, or you can scan your screen and check out our program lineup to see who is speaking. I did see some question in the chat asking if SkyFoundry will be at CX Energy. Yes, they will be exhibiting. John will be there. So we hope to see you there. Thank you again for stopping by, and thank you to SkyFoundry and Energy Twin for sponsoring today.
Thanks so much for the opportunity.
Yeah, thank you very much.
Yeah, and thanks
Bye
for
all.
that great presentation.
Thank you.